Voltage without muscles, when biology becomes a power grid. 800 volts is not a signal, it is a failure state for living tissue at that level. Membranes rupture, timing collapses, coordination disappears. Nervous systems are built to whisper, not to shout, and yet the shouting continues. The electric eel exists in direct violation of what soft biological matter is supposed to tolerate. This animal is not large by industrial standards. It contains no metal, no insulation, no engineered wiring, and still it produces electrical discharges that rival household outlets, not once, but repeatedly, deliberately, as part of normal behavior. This is not an accidental spark. It is a controlled output, and that is where the discomfort begins. Electricity inside living bodies is usually subtle, measured in millivolts, carefully buffered, easily disrupted. Push it too far and muscle fibers lock, neurons misfire, hearts lose rhythm. The eel pushes far past that line and does not collapse. Its body is mostly tail, and most of that tail is converted into stacked electrocytes, flattened cells derived from muscle that no longer contract. They exist solely to hold charge. Each cell contributes almost nothing on its own, but evolution arranged them in series, like biological batteries, summing their voltages into something that should not be survivable in wet tissue. Water is an unforgiving medium for electricity. It disperses energy, it punishes inefficiency, and yet the eel's discharge remains coherent long enough to overwhelm the nervous systems of other animals. This is not strength in the mechanical sense. There is no crushing force involved, only timing. Muscles everywhere rely on precise electrical cues to contract and relax. The eel injects noise into that system, forcing every muscle to fire at once, then fail together. What makes this unsettling is not that it harms other animals, but that it requires the eel to live permanently adjacent to catastrophic electrical conditions. Every discharge travels through the same water, the same body, the same biological environment that most organisms must carefully protect from stray current. There is no visible armor, no thick insulation separating weapon from self. Instead, the eel survives by arrangement alone, by geometry, by orientation, by membranes tuned just enough to tolerate what should overwhelm them. It is a solution without comfort. The eel cannot afford sloppy control, because electricity does not negotiate. A mistimed discharge would not merely miss prey, it would disrupt the eel's own nervous system, its own muscles, its own ability to breathe. This is a body operating without margin, converting metabolic energy directly into electrical force with no mechanical buffer in between. Nothing about this setup suggests longevity or stability, and yet it persists. The eel swims slowly, breathes air, and waits, carrying within it a grid powerful enough to short-circuit animals many times its mass. There is no escalation, no drama in the design, just quiet repetition of a process that should end badly. Biology usually avoids extremes because extremes are fragile. Here, the extreme is the strategy. The electric eel does not flirt with the edge of failure occasionally. It lives there continuously, a soft organism shaped into an active electrical hazard, functioning not because the rules were broken, but because they were followed all the way to a place most life never dares to approach. The cost of a shock, energy burned faster than survival allows. High-voltage electricity is never cheap. Every pulse represents a rapid drain of stored ions, gradients rebuilt molecule by molecule, using chemical energy that took time to accumulate. In most animals, energy budgets are conservative by necessity. Calories are spent on movement, digestion, repair, reproduction. There is rarely room for waste. The electric eel ignores this logic. Each discharge empties electrocytes of their carefully maintained charge, and restoring that charge requires active transport, ATP consumption, and time. From a metabolic perspective, this behavior is reckless. A single strong shock can consume a measurable fraction of the eel's available energy, not gradually, but all at once, like opening a valve instead of turning a dial. In freshwater environments where food availability fluctuates and oxygen can be limited, this should be unsustainable. And yet the eel continues. It does not ration electricity to emergencies alone. It uses it to hunt, to probe, to orient, sometimes firing rapid sequences of pulses that leave its own energy reserves temporarily depleted. Recovery is not instant. After intense electrical activity, The eel becomes slower, less responsive, metabolically strained. This is not hidden damage, it is a visible tax. The unsettling part is that the eel accepts this cost as routine. There is no backup system delivering electricity more efficiently, no alternative low-cost weapon. The entire hunting strategy is built around brief periods of extreme expenditure followed by enforced recovery, a cycle that leaves little room for error. If prey density drops, if recovery is interrupted, if environmental conditions shift, the math stops working. Most animals avoid strategies that spike energy consumption because spikes create vulnerability. During recovery, reaction time slows, escape options shrink. The eel chooses to live in that vulnerability repeatedly. It is not optimized for endurance or efficiency. It is optimized for decisive electrical events that momentarily overpower other nervous systems at the expense of its own reserves. This is biology operating like a device with a limited battery, discharging aggressively without knowing when the next recharge will be possible. There is no conscious budgeting here, only evolutionary persistence of a pattern that happened to survive long enough to reproduce. What makes this uncomfortable is not the spectacle of electricity, but the accounting behind it. The eel's survival depends on the environment continuing to forgive this imbalance, on prey continuing to appear often enough to justify the cost of stunning them. Remove that forgiveness, and the system fails quietly, not with drama, but with depletion. Energy does not care that the eel is specialized. It does not adjust rates or offer grace periods. The eel burns through its reserves because its design demands it, not because conditions are always favorable. This is a life form built around short bursts of metabolic excess in a world that rarely guarantees abundance. It survives not by being efficient, but by spending energy faster than most animals can afford to, trusting that the delay between discharge and recovery will not be fatal. That trust is not enforced by safety margins or redundancy. It exists because, so far, the environment has not withdrawn its permission. Paralyzing giants, when size stops protecting you. Large bodies are supposed to be safer. More mass means thicker skin, deeper muscles, longer nerves, systems that dampen disturbances simply by scale. Most predators respect this rule because they have to, force scales poorly against size. Teeth break, jaws tire, mistakes become lethal. The electric eel does not engage with mass at all. It targets control. When a discharge enters another animal's body, it does not need to overcome strength. It only needs to arrive at the right time. Muscles contract because nerves tell them to. The eel overwhelms that instruction set, flooding the system with synchronized signals that force every muscle fiber to fire simultaneously. The result is not injury in the mechanical sense, it is functional collapse. Even animals with thick armor and powerful limbs, including crocodilians, lose coordination within milliseconds. Their size becomes irrelevant because their nervous systems obey the same electrical rules as smaller ones. This is a violation of an unspoken biological assumption that being big buys time. Here, it buys nothing. The eel's electricity does not care about leverage, bite force, or muscle cross-section. It cares about conductivity and timing. In water, bodies become circuits, whether they evolved for it or not. What makes this unsettling is how little effort is required relative to the effect. The eel does not wrestle, chase, or exhaust its target. It injects a brief electrical event and waits for the inevitable outcome as motor control collapses. The victim is not overwhelmed by damage, but by obedience to its own biology. This exposes a weakness shared by all vertebrates. Muscles are slaves to voltage. No amount of size changes that. From an evolutionary perspective, this is deeply uncomfortable. Many defensive traits scale with body mass, but neural control does not gain insulation as animals grow larger. It remains exposed, distributed, dependent on coordinated electrical signals traveling long distances through conductive tissue. The eel exploits that dependency with precision. It does not need to kill immediately. Temporary paralysis is enough. Gravity, water, and oxygen deprivation finish the process without further input. This is not aggression amplified, it is strategy simplified. The eel bypasses escalation entirely. There is no contest, only interruption. For large animals accustomed to safety through bulk, this is catastrophic. Their evolutionary investments offer no protection against a mechanism they cannot feel until it is already too late. The eel's existence forces an uncomfortable realization. Dominance based on size assumes physical confrontation. Electricity ignores that assumption. It operates at the level of control systems, not structure, and in that domain, everyone is equally fragile. Precision and chaos, electricity that knows where to go. Electricity is indifferent. It spreads, it leaks, it follows paths of least resistance without regard for intent. In water, this behavior becomes even less predictable. Currents diffuse, energy dissipates, signals blur. Under these conditions, precision should be impossible, and yet the electric eel achieves something uncomfortably close to targeting. Its discharges do not simply radiate outward as wasted noise. Through body posture and timing, the eel shapes electric fields so that current density concentrates through the bodies of nearby animals. This is not intelligence in the planning sense, but it is control in the physical sense. By curling its body or aligning itself with prey, the eel increases the voltage gradient across critical muscle groups, effectively turning the victim into the most conductive path available. The water does not protect them. It completes the circuit. This pushes biological control beyond what seems reasonable for an organism without sensors designed for engineering calculations. There is no map of resistance, no conscious adjustment of amperage. The eel relies on consistent physical laws and a body plan that exploits them automatically. The unsettling aspect is how repeatable this is. The eel does not occasionally succeed by luck. It succeeds often enough for the behavior to persist across generations. That implies a degree of reliability in a medium defined by variability. Water composition changes, temperatures shift, bodies differ in shape and size. Despite this, the eel's electrical output remains effective. It does not need perfect efficiency, only enough precision to push nervous systems past their tolerance. This blurs the boundary between biological function and engineered system. Precision is usually purchased with complexity and redundancy. Here, it emerges from simple repetition and anatomical constraint. The eel's body is arranged so that when it discharges, the physics does the rest. That absence of decision-making is what makes it uncomfortable. There is no judgment involved, no adjustment for mercy or error. The eel fires, and whatever happens next is dictated by conductivity. In this setup, chaos is not eliminated, it is narrowed. The eel reduces a messy environment to a single outcome often enough to survive. This is not mastery of electricity, it is coexistence with it at a level most organisms would find intolerable. The eel does not control every electron, it merely releases them under conditions that statistically favor paralysis over escape. That is enough. Biology rarely achieves this kind of repeatable influence over complex environments. When it does, it usually comes with a price. Here, the price is living permanently adjacent to failure, trusting that the same uncontrolled physical laws that empower the eel will not, on the next discharge, turn inward. Self-shock. Tolerance. Living inside your own weapon. Electricity does not distinguish between source and target. In most organisms, even small stray currents can disrupt cardiac rhythm, scramble neural timing, or damage tissue at the cellular level. Exposure scales with conductivity, and living bodies are efficient conductors. By that logic, the electric eel should be its own first casualty. Every discharge it produces propagates through the surrounding water and reflects back through its own body. There is no isolation chamber, no insulated casing. The eel survives by structural compromise. Its vital organs are positioned away from the main electric field, compressed toward the head, while the majority of voltage drop occurs along the tail where electrocytes are densely packed. Even then, tolerance is not immunity. The eel experiences its own electric fields. It simply endures them. Membranes are adapted to withstand repeated depolarization without losing integrity. Ion channels reset rapidly, avoiding the cascading failures that would cripple other animals. This is not a perfect solution, it is a narrow one. Small deviations in timing or intensity could still interfere with respiration or heart function. There is no evidence of large safety buffers built into this system. Instead, there is just enough separation, just enough resistance, just enough recovery time. What makes this unsettling is how little room there is for error. The eel does not possess a second nervous system shielded from its weapon. It has one, and it uses it anyway. This forces a lifestyle of precision not because of awareness, but because imprecision would be lethal. Most animals evolve to avoid conditions that threaten core physiological processes. The eel evolves to operate inside them. Its body accepts regular exposure to forces that, in any other context, would be classified as traumatic. This is not resilience in the comforting sense. It is constant risk management performed at the cellular level without conscious oversight. The eel cannot decide to stop producing electricity without abandoning its primary survival strategy. It must continue to shock, knowing that every discharge carries a small chance of internal disruption. Over time, those risks accumulate. There is no repair mechanism that eliminates them entirely, only systems that reset fast enough to delay failure. The eel lives inside its own hazard, not protected from it, but balanced against it. That balance is not guaranteed by design philosophy or foresight. It exists because evolution found a configuration that fails slowly enough to reproduce. That is the only standard being met. No safety margin, a life designed to sit on the edge. Stability in biology usually comes from excess, extra capacity in organs, redundant pathways, slow tolerances that absorb shock and variation. The electric eel has very little of that. Its entire existence is tuned toward a narrow operational window where electricity, metabolism, and neural control remain aligned just well enough to function. Push any one variable too far, and the system does not degrade gracefully, it fails. There is no secondary hunting method that works at scale, no alternative defense that compensates if electrical output drops. The eel's body is specialized to the point of dependency. Oxygen levels fall, and recovery slows. Food becomes scarce, and high-voltage discharges become unaffordable. Water chemistry shifts, and conductivity changes, alter how electricity moves through both prey and self. Each of these factors eats into the same margin, and that margin is thin. What makes this disturbing is how normal the eel appears while operating under these constraints. It swims slowly, often motionless, giving no indication that its survival depends on continuous precision. There is no visible warning when the balance tilts. Failure does not announce itself. It arrives as missed timing, delayed recovery, insufficient charge, small errors compounding until electricity no longer provides control. At that point, the eel is simply a long, soft fish in an environment that does not forgive weakness. Evolution did not provide it with insulation from this outcome. It provided just enough functionality to postpone it. This is not a life built for comfort or resilience. It is a life built to exploit a loophole in biological scaling, converting chemical energy directly into neural disruption and accepting all the risks that come with that conversion. The eel does not represent an apex in the reassuring sense. It represents a boundary case, an organism demonstrating how far a living system can be pushed toward instability without immediately collapsing. That is where the unease settles. The electric eel is not dangerous because it is aggressive or monstrous. It is dangerous because it proves that biology can function as an exposed, high-voltage system, operating without buffers, without guarantees, balanced permanently at a level where most life would already be failing. It survives not because nature is kind, but because nature is indifferent to how close to collapse a system is, as long as it continues to work.